Welcome viewers and subscribers. Welcome back to another video. JK Engineering and Architecture coming to you again with another engineering video. So in my last video, I have shown you how to calculate the reinforcement for a beam. So we have calculated that to withstand the load of 1 kips per foot dead load and 2.45 kips per foot live load plus the beam's self weight, the reinforcement to withstand those load, the beam is going to need 6 number 8 bars or 6 1-inch bars. So to ensure that the beam cross section is adequate, that the moment capacity or the nominal moment is good enough to carry those loads, I have to carry out certain checks. And one such check is that we have to ensure that our nominal moment is equal or greater than our ultimate moment. So this is supposed to be greater than or equal to mu. So your phi mn must be greater than or equal to mu. So we have calculated our mu, ultimate moment from the last video, to be 508.9 kgs per foot. I know in the final calculation I have written down 589.69. That was written down in error, even though the result is going to remain the same. So this should have been 508.9. 508.9. So I have written down that 589.69 in error, but the result is going to remain the same. So to do that, the nominal moment, which is phi mn, or moment capacity, right? The formula to calculate phi mn is the area of steel times the yield stress of steel times d minus a over 2. And this d here we have calculated last week as our effective depth to be 24.5 inches. So to calculate A is the area of steel times the yield stress of steel over 0.5 times Fc prime B. And Fc prime is known as the compressive stress of concrete, and that is given as 3,000 pounds per square inch or 3 kips per square inch. B is referred to as the width or the breadth of the beam. So B is really 24 inches. So we can now move ahead to calculate our nominal moment. So I'm now going to proceed in calculating the nominal moment or the moment capacity for this beam. So in order to do that, and I've given you the formula already, to be phi mn is equal to the area of steel times the yield stress of steel times d minus a over 2. So we know that the area of steel from our previous calculation to be 4.61 inch square, and we know that the yield stress of steel is going to be 60 ksi, and the effective depth is going to be 24.5 inches. So if you notice A, we do not know A in the formula. So to calculate A is going to equal to this formula here. The area of steel times the yield stress of steel divided by 0.85 times the yield stress of concrete times B. And the yield stress of concrete is given as 3 ksi, and B, which is the breadth, is given as 24 inches. So if you should plug that into your calculator to calculate A, So A is going to equal to the area of steel, which is 4.61 inch square, times the yield stress of steel to be 60 KSI, divided by 0.85 times the compressive stress of concrete to be 3 KSI, times the B, which is the breadth, which is 24 inches. If you should plug that in your calculator, you will get 4.52 inch. So A is 4.52 inch. So having calculated A, I can now proceed to calculate my nominal moment. So to calculate the nominal moment, that is the formula there. I've stated to you already. So the nominal moment is going to be the area of steel, which is 4.61 inch square, times the yield stress of steel, which is 60 KSI, open bracket, minus D, and D is the effective depth, which was 24.5 inches, 24.5 inches, minus A over 2, and we just calculate A. We just calculate A here to be 4.52 inches. So this is going to be 4.52 inch divided by 2. And if you should plug this into your calculator, you will get 7020.11 kips inch. So our nominal moment is going to equal to 720.11 kips inch. But you notice we haven't factored in our phi. So our moment now, and phi for flexure is 0.9, coming from my last video. So we have 0.9 bracket 7020.11 kips inch. But because we are matching our nominal moment to our ultimate moment is given in kips foot. So to bring our nominal moments to foot as well, because this is in inch, kips inch, we have to divide by 12 inch. And if we should plug that in your calculator, you're going to end up with 526.51 kip foot. So our phi mn is going to equal to 526.51 kips foot. So we're going to match this up now. With our ultimate moment of 508. So in order for our beam to be safe in calculating the load, and we know that the reinforcement is good enough to withstand the bending effect due to those loads, our phi mn must be greater than or equal to mu. So if that is not okay, then you have to go back and adjust your beam size. But in this case, our beam is okay because our phi mn is 526.51 kip-ft, and our MU is 508.9 kip-ft. So our phi mn indeed is greater than our MU, therefore our beam is okay. Therefore our beam is okay, because it has satisfied the condition of phi mn is greater than MU. So that takes care of the calculation due to bending. So remember what I've said in the beginning of my presentation in my last video, that when you're designing a beam, you're designing the beam to withstand two scenarios. You're designing the beam to withstand shear, and you're designing the beam to withstand bending. So in this design, we have satisfied, the beam is satisfied in terms of its bending. The 6 1-inch bar can resist the load due to bending, so our beam is okay. So now we have to do our shear reinforcement. And when we talk about shear reinforcement, we are really talking about the spacing of our stirrups. So join me in the next video when I calculate the shear reinforcement for this beam to complete the design of this beam. So as usual, if you're watching this channel for the first time, ensure to subscribe, ensure to hit the thumbs up button and give it a like. For those of you who have clicked on this video, I'm imploring you, asking you if you could just watch the video until the end. Thank you and enough respect.